Thank you, Edouard, for the invitation. In this talk, I want to convince you of the importance of mesoscale processes for meridional transport and for the AMOC. So I am working, and I'm a physical oceanographer and working mainly with numerical models. So I thank many colleagues of the NEMO team, the DRACAR group, or Ocean Model Development Panel that have helped me over the years. The image of the conveyor belt is really very misleading, as has already been mentioned. But I want you to think and imagine what a conveyor belt is, like I don't see whether you can see. Okay. Yeah, okay, you can see my mouse here. So if you see this image, you imagine the conveyor belt. If you put your luggage on the conveyor belt, you hope that your luggage is going to stay there and go straight to its destination. And here is what American colleagues have done, which is to put reinforced floats that are acoustically tracked at depths of 700 and 1,500 meters. So they have put the floats basically on that side of the conveyor belt. And you see that the floats have gone everywhere, all over the place. These are the displacements of the floats, and certainly they go in all directions. And also they follow very wiggly paths because they are affected by the ocean mesoscale. So this prompted Susan Lausier to say that we need to deconstruct the conveyor belt. So this is what I want to do in this talk, to tell you how mesoscale AD deconstruct the AMOC, and start with thinking about what mesoscale ADs are, their role in meridional transport, in AMOC variability, and in projecting the future AMOC. So first, let's look at ocean eddies, because they are so beautiful. This is a picture from space altimetry by NASA. And you see that, I shouldn't interfere. So you see that eddies are everywhere. You are here in the North Atlantic. You see the Gulf Stream with meanders, closed eddies. So this is a warm branch of the AMOC. We are going to go down, and you will see also eddy shedding in the North Brazil Current here. So all along the path of the AMOC, you have those eddies, and they are the most energetic mode of variability in the ocean. This is really what dominates the ocean circulation. Here also the Agulhas eddies in the South Atlantic. So I will stop the animation here. But where do these eddies come from? So it is useful to take a laboratory experiment. So here there is a reservoir filled with water, and it is rotating like our planet. And there are different temperatures on the interior side of the reservoir and the exterior side. So this difference in temperatures sets up a circulation around the tank, but it isn't stable. And soon you see in the rotating tank, these meanders develop. This is what we call baroclinic instability. And this is the main source of energy for the ocean eddies. It is also very important in the atmosphere. You can think of the similarity between this picture of the lab experiment with the meanders developing and and the atmosphere here. So this is a map of the pressure at 500 millibars, and the North Pole is in the middle. And you see those meanders in the atmospheric circulation that are the disturbances that make our weather, and that are why our weather is variable from day to day. The difference between the atmosphere and the ocean is the size of eddies. In the atmosphere, disturbances have a typical scale of 1,000 kilometers, but in the eddies, they are much smaller because the ocean is denser. And here you see it in this image of the Antarctic circumpolar current with Antarctica in the middle. And you see that the meanders and little eddies everywhere are much more numerous than in the atmosphere. In fact, they are much more interesting in the ocean for that reason. So I would skip that one just to say that the eddies are very nonlinear, and so there is also all this question of sensitivity to initial condition, chaos, feedbacks between the mean flow and the eddies that come into play when we study them. So we see eddies, when we look at the ocean from space, we see eddies all along the path of the AMOC. Here we see them in the Agulhas, born in the Agulhas retroflexion and propagating in the South Atlantic. Here we see them in the Gulf Stream, looking at the temperature from space with a cold eddy here, for example. And we also see it in this very important region of the Labrador Sea, here seen in the sea color. And you can see that in the Labrador Sea, the eddies are much smaller because the typical dynamical scale, which is called the Rhodesby radius, is smaller in regions closer to the poles. And so the eddies are everywhere. So why are they important? One first thing is the role that they play in meridional transports. And to look at their role in the meridional transport, because observations are difficult, it is mainly been studied in numerical models, at least globally. One way to quantify what the eddies do is to consider the fact that if you transport temperature, so it's a product between the temperature and the velocity, and if you take an average of that to have a kind of representation of a mean ocean circulation, it can be thought as a mean over a very long time without climate change, possibly, and or a mean between an ensemble of different simulations with different random eddies. But if we take the mean, then we see that the total transport of heat, the average of VT, is simply the sum of the transport of the mean temperature by the mean flow, V bar, T bar. Here the mean is represented by the over bar, and a term which is the average of the correlated velocity temperature fluctuations. And this term is usually non-zero, and it can be used to quantify, to give us an impression of how important the eddies are to transfer properties in the ocean. So here the eddies flux have been estimated using a 1/12 of a degree, that model that Juliette has shown already. So it's a model with 8-kilometer grid at the equator and 4-kilometer grid in the northern latitude, with 8-kilometer grid with eddies that have diameters of 100 to 300 kilometers. You are starting to resolve them. It is not so true in the Labrador Sea, where the eddies are really very small, and 4 kilometers may not be enough. And this contribution along this line here can reach 0.2 to 0.35 petawatt, this V prime T prime. So that's about a quarter of the total northward heat transport in this latitude band. What these models reveal is that the eddy contribution is different at different latitudes. It is also very important in the Antarctic circumpolar current, but at the latitude of the rapid array, where the MOC is measured at 26 north, the eddy contribution is in fact close to zero, and it's very small, which is very convenient because otherwise the rapid measurements would not be very reliable. So eddies transport heat, and what about salt? You have seen that the AMOC carries warm and salty water northward, and we see that the eddies have a signature in salinity as much as temperature. This is a map from a satellite observation with a small satellite that is able to actually measure the salinity of the ocean from space. And you see that the eddies are also anomalies of water less salty or saltier than their environment. So to understand the way eddies, the part that eddies play in the transport of salt, we have First, to understand why there is a transport of salt in the ocean. And this transport is forced by the evaporation, precipitation, and runoff at the surface. So here I am thinking as a function of latitude from the South Pole to the North Pole. And so that's why I have put this map of evaporation minus precipitation in the wrong direction. Well, what we usually think as the wrong direction. So you see that in the southern latitude, it's blue. This means that there is mainly precipitation. There is water coming from the atmosphere. Then in the subtropics, it's evaporation. It's red. The water is coming from the ocean into the atmosphere. In the equatorial regions, it's again precipitation under the intertropical convergence zone, the ICTZ, and then again evaporation, and then precipitation. And this creates a volume flux in the ocean. Why? It's because, I mean, when you evaporate water, of course, you are not going to make a hole in the ocean. Very soon, the hole will be filled by water that moves around through pressure forces. Water can move around very fast through pressure forces in the ocean. And the typical example is tides. A tidal wave can go around the ocean in less than 12 hours. So then there is this volume flux. It is expressed here in the usual unit for oceanographers, which is Sverdrups, which is a million of meter cube per second. I will come back where I was. And so it's small compared to the overall MOC because it's just one Sverdrup. So it's not very important for the MOC itself, but it's important for the salinity of the ocean and to understand how the salinity changes, because this is a transport of this transport is important for salinity. And so when we look at this transport here, it increases and decreases. And what is the most important is the derivative, in fact, of this curve, that is whether there is divergence of water or convergence of water. And you see that the subtropics in red here are also indicated in red. This means that you need to have a convergence of water to support the constant evaporation in these places. So this means that this constant influx of water, this convergence, brings in salt because the water is salty. And this is just a top-to-bottom ocean transport. So we can know very well from observations, because we have observations of E minus P minus R, and from the salinity, we can see what is this salt transport, which is in fact a forcing that somehow you have to balance. Otherwise, your subtropical gyre here, because there is convergence of salt, would become saltier and saltier and saltier and never equilibrate. How does it equilibrate? It equilibrates because currents in the ocean move salt around, but also because the eddies move salt around. And so what we have done is, again, we have this black curve, so that is what we need to equilibrate. And there are two ways we are equilibrating this curve. One is by the black curve, which is the mean currents, like the fact that the Gulf Stream is salty and there is a current coming back, which is perhaps a little less saltier. And the blue is the eddies. So you can see, for example, between 10 to 40 north, that's a subtropical gyre of the northern hemisphere. You have this convergence of salts that must be equilibrated, and it is equilibrated perhaps mainly by the black line, which is the mean flow, but almost as much by the eddies. And for example, at 40 north here, you see that the eddy contribution is as large as the mean, and it's about the same at 40 south. So for the heat, we have seen that about 1/3 of the total northward heat transport was due to eddy velocity temperature fluctuation, somewhere between 20% and 1/3. But for the salt, it's even more important, and eddy fluctuation perform half the northward transport of salt that we need to compensate the E minus P minus R, the evaporation, precipitation, and runoff. But The effect of eddies is more complicated than this convenient term, this V prime, T prime, or V prime S prime that we are measuring, because the eddies move and they carry with them water mass properties. For example, if you remember these Agulhas eddies that you have seen in the movie, they are formed here in the south of Africa, and then they travel in the South Atlantic. And inside the eddies, they carry Indian Ocean waters that are warm and salty. And this complex transport, this Lagrangian transport, cannot be represented very well by just looking at a V prime something at one place. And more difficult even is the fact that we cannot parameterize. We really don't know at all how to parameterize something as complex and non-local as one eddy taking properties from the Indian Ocean and carrying it all the way to the Brazilian coast here. So this is a big challenge, in fact, for climate model, this non-local properties of the eddy transport. Now I will move to the variability of the AMOC. Can eddies also call temporal variability in the AMOC? We have seen that the eddies contribute to the meridional transport, that are the main role of the AMOC, and they can also cause temporal variability. And I just want to point out that, I mean, you have seen this picture from Lynn Talley already, and you see that she has already started a little bit to deconstruct the AMOC by putting the Agulhas eddies here instead of a kind of conveyor belt-like branch. So to quantify the eddy-induced variability, I will use models also. First, I want to have you remember that the ocean eddies have a typical time scale of a few months. And space scale, we talked about a diameter of 100, 200 kilometers, more or less. But because there are nonlinear energy transfer, this means that these eddies can induce variability in the ocean at much longer time scale and much larger space scale. So this is what we want to quantify here. And this is work that has been carried out by Thierry Penduf and collaborators. They took two numerical simulations. One was an ocean ice model forced by the atmosphere. So one of those models that Julie talked about. You take the observed state of the atmosphere to force the ocean. So you have all the time scale of variability of the atmosphere from 1 day to 50 years. And then you take the same ocean ice model, but you force it with a repeated seasonal cycle of the atmosphere. So in this second model, if you end up finding in the ocean variability at scales larger than 1 year, it will be entirely generated by the nonlinearity in the ocean. So this is what Thierry Penduf calls intrinsic variability, and this is what we are going to try and quantify. So here, the first two graphs show model 1 and model 2. And what is shown is a contribution to AMOC in sphere drops. The unit should be familiar by now, as a function of latitude. So we are in the Atlantic from 30 south to 70 north. And we are looking at the standard deviation of the variability in the model for periods from 2 to 32 years. So it's a long period, longer than the typical eddies. We see a lot of variability in the model with complete atmospheric forcing. This is not surprising because all those time scales are present in the atmosphere. And here in the model with seasonal forcing only, we still see variability. And this variability is the intrinsic variability that is entirely generated by the turbulence in the ocean. And you see that it's of the same order of magnitude than the total variability. And when we take the ratio of the two, we have the percentage of intrinsic variability, which is the percentage of variability in the AMOC that is forced by random eddies. So when we talk about trying to find the cause of variability of the AMOC, we need to remember that at some latitudes, at least, a very significant part is just randomly created by a bunch of eddies. Of course, this percentage can be 40 or 50% in near the Agulhas eddies, because basically the warm branch of the MOC there is nothing but eddies. It's also quite significant in the Gulf Stream, 30 to 40%. It's less significant at other places. And here, what you have, the different curves represent different models. They are modeled at different resolution, but what you see is the 2-degree model, the red one, has really zero intrinsic variability, which is normal because at 2 degrees you don't resolve the oceanic eddies, you must parameterize them. And so all this intrinsic variability of the EMOC is gone in this low resolution model. So Thierry Benduf has also, and Sandy Gregorio have also looked at the patterns of and the coherence of this EMOC variability, this intrinsic variability. So here you see, as a function of the year and latitude, the propagation of the signal in the 15-30 years band. So there has been a bandpass filtering of this variability. And in the 15-30 years band, you see that it's mainly originating from the south. And this impact of the Agulhas eddies, by the way, had been already shown by Arne Biastok in 2008. And there is a lot of northward propagation, but the propagation can reverse occasionally. And so there is a range of propagation speed of these anomalies along the path of the EMOC from the south to the north. And for the 50 to 90 years band, the variability, in fact, is larger in the northern hemisphere and between 30 north and 30 north. It is also quite smaller. So to finish on the variability of the EMOC, I want to say a word of the variability of the Atlantic inflow into the Arctic. That is something which is very important, especially in a changing climate. There are two branches of the North Atlantic Current and the EMOC, two branches that enter the Arctic. One goes through to the Barents Sea, and the other one here goes through Fram Strait. So I have diagnosed these branches in a coupled 1/12 of degree ocean model. So we are again at a resolution of about 4 kilometers here in the Nordic seas. And this model was run by the UK Met Office. So the first thing, unfortunately, to realize is that in the Nordic seas, the typical eddy scale, the Rossby radius, is very small, which means that it's perhaps like 10 kilometers, which means that with 4 kilometers, we are not still resolving the eddies enough. Most of the warm water circulates in very narrow currents in the Nordic seas. Here, this is a Norwegian slope current, which is an unstable current and creates eddies. And you can see these eddies in observations from drifters, surface drifters. This is the eddy kinetic energy. So there is a big patch here in the Lofoten Basin. And in the model, the patch is not present. So there is eddy generation. If you look at snapshot, you see eddies being generated, and you see a lot of variability in this Norwegian current. But still, we have not attained the degree of realism that we would like, even at this high resolution. What we have done was to compute a complete budget of heat in the Nordic seas from this model. And the main results are that eddies fluxes are very important at two locations. One is the recirculation of warm water above Knipovich Ridge south of Fram Strait. So this is Fram Strait, this is the branch entering the Arctic, and this is the branch entering the Barents Sea. And we have a strong recirculation here with about 20% of it due to eddies. And eddies are also important in Denmark Strait. This is something that is been already shown from observation. So this means that if you try to understand the heat balance in this key region of the world, especially the Greenland Sea, where you have deep convection and formation of deep water. So if you want to try to understand the heat balance of this part of the Nordic Sea, the Greenland plus Iceland Sea, well, the convergence of heat into these regions is 25% eddy-driven. So it's a very important signal. And in observations, what happens also is that this eddy signal makes it much more difficult to understand long-term variability. For example, we have looked at the correlations at interannual timescales between the variability of this branch entering the Barents Sea and this branch entering Fram Strait. And there has been some literature about correlations and time lags derived from low-resolution climate models. But the correlations are very different at high resolution. Sometimes there is a lack of correlation. You don't find this correlation anymore because it is obscured by eddies. And so I would argue also that if you try to understand how the variability of these warm branches of hammock is going to impact, for example, the Arctic sea ice, you really need to take eddies into account because you may overestimate your capacity to predict, your predictability. Finally, I will talk a little bit about projecting the future AMOC and what could be the role of eddies and fine-scale dynamics on the AMOC evolution in the changing climate. So the processes also where, of course, where eddies come into play are numerous, and many of them have already been mentioned in the previous talks. We've seen that the Labrador Sea, for example, is full of eddies. So if you form water in the Labrador Sea, this formation will be influenced by the eddies. And same thing for the Nordic Sea, as we have just seen. And so the only way we have to try and look at this in the future is numerical models again. So you have already seen this plot. I think Pascal showed it. It's from a paper by Wagers, where they looked at the CMIP6 models. So those are models with either low resolution or moderate resolution. And they found that the decline in AMOC was projected in all the scenarios. So in 2100, at the end of the century, they project a 24% decline for good scenario where we follow the Paris Agreement, and 32% decline if we are on a not so good path. They also found that in many models, the decline is related to the historical AMOC strength, so that model with more realistic AMOC strengths seem to have a stronger decline. Now this behavior of the AMOC has been recently revisited by Malcolm Roberts and collaborator using a higher resolution model that are also a part of this CMIP model intercomparison exercise, but one called high-res MIP, which means that we are using the highest possible resolution models. So in high-res MIP, first, you have to realize that until now, the protocol for these high-resolution models was to run scenarios only up to 2050, because the model is so costly that it was not possible to run them all the way to 2100. Also, with those models, we have not been able to explore many scenarios. Only the worst possible scenario is being explored. And the figures here show the result, the main result, which is the variation in the AMOC, so the AMOC decline, as a function of model resolution here. So you have the typical climate model with 100-kilometer grid that show different degrees of decline. But overall, there is a clear decline. And here you have the about 20-kilometer models. So those are the models that Juliette was showing an example of. So in this example of the IPSL model, the mean AMOC was not changed very much, and so it's probable that the projection would not change very much either. So there are some models that look a bit the same as the 100-kilometer model, but there is a number of models here that really show a much larger decline of the AMOC compared to the low-resolution models. So definitely there is something happening with model resolution. And then what is also very interesting are the two highest resolution models. So those are the models that we can imagine are resolving the eddies in the very large part of the world. So one of them is this one. It's the Orca 12 model that I have shown before, run by the UK Met Office. It is with 8-kilometer resolution at the equator, 4-kilometer in the northern latitudes. We can think that really the ocean is quite well resolved. And this one in the NCAR model at 1/10 of a degree, which is quite similar in resolution. And the problem is those models give completely different results. I mean, in both cases, the AMOC is stronger at high resolution in those two models. That is what Julie showed, Juliette showed that when you go to a higher resolution, the AMOC tends to be stronger and more realistic. So both the two models there have a stronger AMOC. But then, in terms of decline in the future, they are completely different. And so far, the analysis that is published in this paper is not completely convincing or is not complete, because, in fact, although they have run a very detailed analysis of this model, for example, they can explain why the decline is so large. In their point of view, they have compared along the rapid array all the different components of AMOC using the same software to compare exactly the observation and the model. And what they think is that, in fact, there is a strong decrease in the Florida current going northward, which is not compensated by a return flow. Also, in the low-resolution model, this decline in the Florida current is compensated by the return flow. But it's difficult to tell what is happening in the NCAR model because they have not been able to carry out this very detailed analysis of this model. So it is pretty much an open question. And we need to study more the dynamical effects at high resolution and the impact for future climate. We need to study more the influence of Greenland melting, because we see that when there is melting of the Greenland ice sheet, the spreading routes of this perturbation of freshwater perturbation is going to be very different at high resolution and low resolution. We know that already from forced model, but we need to see what happens in coupled climate models. We need to look at the effect of inertial recirculation gyres and what we call eddy saturation effects. I have not talked about this because I have concentrated on the North Atlantic for lack of time, but really perhaps this is the most important effect of eddies in terms of climate. It is observed in the Southern Ocean, and because of this eddy saturation effect, it means that when you increase the wind in the Southern Ocean, you don't increase the strength of the current, because the energy you put is very quickly transferred to eddies through the mechanism of volcanic instability. So we need to look at this effect. It may be also perhaps a bit behind this difference that we see in the two high-resolution models from NCAR and from the Met Office. Deep water formation is preconditioned and controlled by eddies, so we need to look at that better. And also the deep overflow, we can hope that there is a better representation of flow topography interaction and overflows at fine scales, although this is not always true. But all these dynamical effects are to be studied further in a new European project that Malcolm Roberts has put together, and which is called ERI, and in which there will be more high-resolution models, and there will be projections to up to 2100. So that will be more a better look into the future. So I come to my conclusions. First, the EMOC is not a conveyor belt, because eddies and nonlinear recirculation exist all along its path. The meridional transport of heat and salt, especially at the boundaries of the subtropical gyre, for example, latitude around 40 degrees north in the North Atlantic, are in a large part controlled by eddies. Eddies also affect the variability of EMOC and of the transport at interannual to decadal timescales, even though the eddies themselves have timescales of a few months. Because of those nonlinear cascades, we see that they can affect the variability of EMOC at much larger scales. And then we do not know yet how ocean eddies and fine scale affect the response of EMOC to anthropogenic climate change. So you see after this morning that we are not in a very good situation, because Pascal told us we don't know whether the EMOC is increasing, decreasing, or staying the same. And I am telling you that we don't know yet how the ocean eddies that are very important will influence in the future the response of the EMOC to anthropogenic climate change. Thank you.